Hi everyone! In this video we look at the substitution of alcohols to form alkyl halides. We will be able to prepare alkyl iodides, bromides, or chlorides from these reactions. Here we'll focus on acidic conditions for this transformation. Why do we need acid to take an alcohol to an alkyl halide? I'd like you to first consider this scheme, and please answer these few questions before we get started. Overall, in a substitution reaction, a nucleophile replaces a leaving group. Here we can see that chloride has replaced our hydroxyl group. So in dissecting this, we can ignore any metal ions as they are simply there to balance the charge between any anionic species. Chloride, having excess electrons, is our nucleophile, and the group that is functioning as a leaving group is our hydroxyl group. It leaves as hydroxide. We know that hydroxide is a strong base because the pKa of water is 15.7. It is greater than 11, so we know hydroxide is a strong base. Compare that to chloride, where the conjugate acid pKa is -8. It's a very weak base. This reaction will not get off the ground because we are producing a stronger base than my nucleophile. What can we do to get this reaction to go from alcohol to alkyl halide? Well, one strategy is to make our hydroxyl group into a good leaving group. We can do that with acid. Strong acids, like HCl to make alkyl chlorides, or HBr, HI for making other alkyl halides, are going to protonate. And protonation of this hydroxyl group makes a good leaving group, water, which is a very weak base. This reaction scheme here is a great overview for this reaction. We take an alcohol and we treat it with strong acid, like HCl, HBr, or HI, and we make an alkyl halide. Experimentally, when we run this reaction in the lab, we find that tertiary alcohols react fastest over secondary or primary alcohols. In fact, with a secondary or primary alcohol, quite often you need to heat these reactions to get the alkyl halide product. In future videos, we'll see other ways to take secondary or primary alcohols to alkyl halides. Before we go on, let's look at a few more examples of alcohols reacting with strong acids. In these next few examples, we'll look at the stereochemistry of these substitution reactions. In our first example, we have a chiral alcohol, and when we do our substitution reaction, what we find in the lab is that we get a mixture of two stereoisomers. So the reaction produces all of the possible stereoisomers, so we cannot claim it to be stereoselective. What is the relationship between these two products? These two products are in fact enantiomers, and we would define this mixture as racemic. In our second example with cis-4-methyl cyclohexanol, how many possible products can be produced? In this reaction, we produce two stereoisomeric products. We can have the chlorine coming towards you or going away from you. These two stereoisomers are diastereomers. They're cis-trans isomers of one another. They are non-superimposable, but they are not mirror images. In our final example, what we isolate is a tertiary alkyl bromide. How would we get a tertiary alkyl bromide from a secondary alcohol? From a rearrangement. This is yet another clue that hints towards our mechanism. The fact that we observe mixtures of stereoisomers as well as these skeletal rearrangements points us towards a carbocation intermediate in that mechanism. We'll study the curved arrow mechanism in a later video. Thanks for watching.